All right, thank you for the introduction. It's my honor to present our paper, Harnessing Ray Tracing for Efficient Sparse Matrix Computation. We are living in the new golden age of computer architecture. We hugely rely on building specialized hardware accelerators to improve application performance. However, beyond the engineering efforts, adding a brand new accelerator in a computer system also increases the manufacturing costs and embodied carbon emission. So, instead of designing and adding a new accelerator, an alternative is to fully exploit existing accelerators for multiple domains workloads. In RTSpMSpM, we exploit an ubiquitous hardware accelerator, ray tracing accelerator, to improve the performance of a popular candidate of building new accelerators, which is the sparse matrix multiplication. In this talk, I'll show you, even without any hardware modification, simply by reducing sparse matrix multiplication to a ray tracing problem, we can achieve a 1.85 times speedup over the state-of-the-art GPU library. And if we extend the architecture with just 0.2% area overhead of a GPU, we can achieve more than 3 times speedup. Matrix multiplications are frequently used linear algebra operations in many application domains. However, as the dimensionality of this set grows, the matrices representing application data become sparser and sparser. Therefore, operations on sparse matrices are increasingly common in artificial intelligence applications, especially those using large models, scientific computing applications, including biological and quantum simulations, graph problems like social network mining or network routing, as well as database operations. However, the significant amount of zeros can lead to unnecessary computations. Thus, programmers have been working on efficient algorithms that only computes on pairs of non-zeros in the source matrices for decades. However, existing software solutions on sparse matrix multiplication still underutilize modern GPU vector cores or tensor cores due to 2 main reasons. First, their non-zero entries are scattered in memory, so when we multiply or traverse them, we constantly jump to random locations. This destroys caching efficiencies and leads to irregular memory accesses. Second, every row or column might follow a different computational path depending on where the non-zeros are. This causes control flow divergence, which is excessively painful for SIMD processors like GPUs that relies on synchronized execution. Now, in the new golden age of computer architecture, building accelerators seems to be the only option given the significance of sparse matrix operations. However, building dedicated hardware accelerators for SPM is also less ideal for the following reasons. First, they take up a lot of chip area, often tens of square millimeters. This directly increases manufacturing cost. Second, they're expensive and time-consuming to design. Creating custom hardware means going through long design and verification cycles. Third, they're inflexible. These accelerators are built for only a single job. So if the workloads evolve, or if your application changes, that silicon becomes wasted space. And finally, each new accelerator brings new demands in hardware-software interface. In addition to the programming efforts, there also exists costs and overheads in new runtime or programming frameworks. So, rather than starting from scratch, we ask the question, why not reuse what's already there and make it better? In the rest of the talk, I'll show you that the opportunity of reusing accelerator does exist in modern GPUs, and that's the ray tracing accelerator. Then, I'll talk about how we can reduce sparse matrix multiplication as a ray tracing problem to develop a pure software solution. Through real system evaluation on existing hardware, we've learned valuable lessons and inspire us to develop a minor architecture extension. I'll show you that this minor extension can help us getting close to hardware accelerator performance. And finally, we conclude this talk. Ray tracing is a rendering algorithm that simulates realistic lighting by tracing the path of rays from camera through pixels and into the scenes. testing for intersection with these objects in the scenes. As illustrated here, the ray tracing algorithm generates view rays in red from the camera through each pixel of an image. If these rays intersect objects in the scene, additional rays, shadow rays in black, are cast toward the light source to determine lighting and shadows. Now let's quickly go through the software ray tracing pipeline. It begins with ray generation, where rays are created from the camera and into the scene. Next is the scene traversal stage. Here, the program navigates the rays through each scene object to identify potential intersections. When potential intersections are found, the code will perform an intersection test to confirm hits. Depending on the test result, if there is a miss, the pipeline triggers the miss shader, and if there's a hit, the code would trigger either the closest hit shader or any hit shader. Since the density of objects in three-dimensional scenes are generally sparse, ray tracing algorithm inevitably creates many irregular memory access patterns, as we need to store objects in compact memory formats that trace memory locality with space. And as a ray may or may not intersect with an object, or even after intersection, the triggered rendering effect may vary. The algorithm also creates many conditional computations. Both problems exist in sparse matrix multiplication as well. And again, existing GPU cores and tensor cores cannot handle this type of workloads very well. As the demands of various types of reality application emerge, ray tracing becomes an important software component to offer satisfaction in user experience. To address the irregular memory access pattern and control flow divergence problem, ray tracing accelerators, RTAs, have quickly become standard components in GPUs. Famous examples including NVIDIA's RTX series or AMD's RDNA architecture. So in other words, they're present today in millions of GPUs worldwide. Modern ray tracing accelerators accelerates the process of traversals of scene objects and perform intersection tests efficiently. Depending on the traversal result, the ray tracing hardware can help group instances triggering the same shader functions on the same streaming multiprocessors. This will address the control flow divergence issue while maximizing the utilization of existing GPU hardware. Modern ray tracing accelerators improve the performance of scene traversals and intersections through 1. Constructs bounding volume hierarchy trees that groups scene objects into bounding boxes, and 2. Perform tree traversals and ray box intersection in hardware. The test can finish earlier if there is no further intersection with a box. Once the rays reaches a leaf node in the tree, the hardware can perform ray triangle intersection tests to more precisely approximate the object shape. The right side of this slide shows the pipeline in the ray tracing accelerator to perform ray box intersection test. The pipeline will contain ALUs to perform vector subtraction, inversion, multiplication, as well as comparisons on three-dimensional coordinates of the source points, the bounding box corners, and the direction of the rays to decide if the rays will intersect with a bounding box. As we learned the similarity between SPM-SPM and ray tracing, now I'm going to show you how we can make SPM-SPM a ray tracing problem. So the basic idea is to consider one input matrices as rays and the others as objects. In this example, we represent elements of matrix A as rays traversing the scene, and we treat the elements of matrix B as objects placed within the scene. As there are only 2 dimensions of matrix coordinates, we simply map each non-zero element into a 2D space in the ray tracing problem. And for each non-zero elements in matrix A, we create a ray that shoots toward the north side of the scene from the x coordinates that's identical to the column index of the non-zero elements. After remapping non-zeros as rays and objects, the ray tracing algorithm traverses through the objects, which is the matrix B elements, and an intersection indicates positions where multiplication should occur. With the modern RTAs, this part of the workload will be accelerated by the ray tracing hardware. The triggered computation will perform pairwise multiplication of values attached to the corresponding elements and accumulates the results in corresponding matrix data structures. In modern architecture, this part can leverage conventional GPU cores. So based on the concept of mapping SPM-SPM into ray tracing problem, we create a software implementation where you may find through our GitHub repo and evaluate the performance using an NVIDIA RTX 4090 GPU card with an Intel Core i7-14700K processor. This figure shows our experimental result. So on the horizontal axis, we have the name of the datasets we evaluated through multiplying each dataset themselves. And the vertical axis shows the speedup we achieved by comparing with the baseline, the NVIDIA's Sparse library at version 12.5. On average, we achieved a 1.85 times speedup and shows no slowdown without any hardware modification. After carefully investigating the performance counter statistics, we identified two main sources causing the underutilization of GPU hardware. First, unlike conventional ray tracing rendering algorithm that can trigger many complex computation in their shader functions, matrix multiplication only requires two operations that contribute to the final result. So in other words, the overhead in launching the shader instances, as well as the code that sets up the stage for meaningful computation, is wasteful. The short shaders also causes lots of idleness. And second, as both the ray tracing accelerator and the regular GPU vector cores needs to access the coordinates information, this current algorithm will cause duplicated access to the same set of data. This increases the amount of memory accesses. And furthermore, since ray tracing accelerators and vector cores are separated, they will contend with each other when accessing memory. Since the source of inefficiencies come from the fact that separation of intersection test and triggered shader function, a better design option is to fuse the compute unit performing the matrix multiplication. Now, the code does not need to transfer the multiplications and accumulations to another unit. Therefore, we can avoid redundant computation for indexing and avoid redundant memory accesses. Let's see how we can accomplish that in the hardware for further acceleration. Again, to achieve the better design for SPM-SPM on existing ray tracing accelerators, the hardware needs additional support for multiplication and accumulation. If we naively add circuits for multiplication and accumulations in ray tracing accelerators, this overhead will be significant, especially for the multiplications. So the question becomes, is there a way to do this with low hardware costs? And fortunately, the ray tracing pipeline already contains what we need. Since matrix multiplication only needs 2 dimensions to describe the index of an element, all the z-axis coordinates will become zeros and leads to non-operations when we use ray tracing accelerators for my sparse matrix multiplication. So within the ALUs, there is indeed an ALU for a multiplication that always receives zeros as inputs. Thus, we can leverage that. Therefore, we add an additional control signal and wires to support a Raybox 2D operation that can perform intersection on 2D coordinates, but also perform multiplication that can propagate to the end of the pipeline for accumulation. Now for the accumulation process, RT+SPM-SPM uses a dedicated accumulation engine. To simplify the design of accumulation unit, we restrict accumulation engine to accumulate result in a buffer for a single roll during a window period of time. The hardware accumulation engine asynchronously accumulates the result from the output queue of RayBox 2D coordinates. This manages current results via hashing and performs atomic commits to memory. The runtime will schedule ray generated from the same roll to the same ray tracing accelerator and the same accumulation engine. This helps to reduce the case of switching between during result rolls. There still exists parallelism among multiple accumulation engine and ray tracing accelerators. This is how we were able to add only 0.2 area overheads, and let's see what this hardware can do. So overall, our optimized approach achieves an impressive average speedup of 3.06 times compared to the state-of-the-art sparse matrix multiplication software library, Sparse. Remember, we only incur 0.2% overhead to a GPU. For additional context, we've also included results from Gamma, a state-of-the-art dedicated sparse matrix accelerator. As shown, our methods provide substantial speedup while reusing existing hardware resources, highlighting its performance and resource efficiency. So here's a summary of our contribution. We have a pure software implementation achieved a 1.85 times speedup compared to the state-of-the-art SPM-SPM library, purely leveraging the existing ray tracing hardware. We also have a hardware optimization, introduced only 0.2% additional chip area overheads while delivering a 3.06% times speedup against the state-of-the-art SPM-SPM library. We also achieved a 80% performance per area compared to the dedicated SPM-SPM accelerators. So the takeaway is, reusing widely deployed ray tracing accelerator significantly boosts performance and resource efficiencies for sparse matrix computation. Thank you.